Hello. Today's lecture is on stream ciphers. These are symmetric key encryption schemes that generate a key stream from the secret key, which is then added to the plaintext one bit at a time. I'll begin by presenting the one-time pad, which provides perfect secrecy but is impractical. And then we'll see ChaCha20, which is a widely deployed stream cipher designed by Dan Bernstein. There isn't much I can say about the security of ChaCha20, except that it's been analyzed by many experts over the years, and no security weaknesses have been discovered as yet. There are two types of symmetric key encryption schemes: stream ciphers and block ciphers. A stream cipher encodes the bits or letters of the plaintext one at a time. On the other hand, a block cipher splits the plaintext into blocks of a fixed length, for example 128 bits, and performs the encryption and decryption one block at a time. The one-time pad is a symmetric key encryption scheme invented by Vernum in 1917. The secret key is a random string of letters. By random, without further qualification, I always mean uniformly and independently at random. Here is an example of encryption. Plaintext is written in English. The secret key is a random string of letters of the same length as the plaintext. Encryption is addition of plaintext letters and key letters, one letter at a time, to get ciphertext letters. Decryption is subtracting key letters from ciphertext to get the plaintext. One major disadvantage of the one-time pad is that the secret key is of the same length as the plaintext. This is especially inconvenient if Alice and Bob are exchanging long messages over a period of time, and so it might be tempting in practice to reuse the secret key. But this should never be done. To see why, suppose that a plaintext M1 is encrypted with K to get ciphertext C1, and the second plaintext M2 is encrypted with the same key K to get ciphertext C2. Then an eavesdropper who sees the ciphertexts C1 and C2 can subtract them. The K's cancel, and the result is M1 minus M2. So the eavesdropper can compute M1 minus M2, which depends only on the plaintexts M1 and M2, and not on the secret key. Thus, C1 minus C2 can leak information about the plaintext. For example, if the adversary happens to know a few of the letters in M1, then the adversary can immediately compute the corresponding letters in M2. In the one-time pad, we took the plaintext letters to be the English alphabet. From now on in the course, unless otherwise stated, messages and keys will be assumed to be binary strings, also called bit strings. This is a reasonable convention since computers process binary data. I'll use this XOR symbol, XOR standing for exclusive OR, to denote bitwise exclusive OR, or XOR in short. This is bitwise addition modulo 2. For example, you can check that the XOR of these two binary strings gives you this binary string. You can also check that the binary string X plus itself equals 0. And this is because 0 plus 0 equals 0, and 1 plus 1 equals 0. Also, the XOR operation is commutative. And so, you can manipulate equations like this one that involve XOR just by treating X, Y, and Z as binary vectors. With our convention, we can express encryption for the one-time pad as simply C equals M plus K, whereas decryption is M equals C plus K. Here's a cute example which illustrates very nicely why reusing a key in the one-time pad is something you should never do. I have the plaintext message M1 as an image, but you can think of the message as a binary message by treating each black pixel as a 1 and each white pixel as a 0. Similarly, here I have the secret one-time pad expressed as an image. So then, the sum of the plaintext M1 and the key K gives us the ciphertext C1, shown here as an image. Next, I'll use the same key K to encrypt the second plaintext M2 to get ciphertext C2. Note that each of the two ciphertexts appear perfectly random and hide the corresponding plaintexts. However, if you add C1 and C2 together, then since K plus K is a zero string, their sum would be M1 plus M2. And so by adding the two ciphertexts together, one can actually see both of the plaintext messages in the resulting image. And this shows that the secret key in the one-time pad should never be reused. The one-time pad is information theoretically secure, and so it is perfectly secure. More precisely, the one-time pad is semantically secure against ciphertext-only attack by an adversary with infinite computational resources. This claim can be formally proven using concepts from information theory. This was first done by Claude Shannon in 1949. The bad news with perfect secrecy is that Shannon proved in 1949 that if plaintexts are L-bit strings, then any symmetric key encryption scheme that has perfect secrecy must have a key space of size at least 2 to the L. And so individual secret keys must on average be of length at least L bits. This means that secret keys must be at least as long as the plaintext. Hence, symmetric key encryption schemes that possess perfect secrecy are impractical. However, all is not lost. The one-time pad provides the inspiration to construct so-called stream ciphers. The basic idea of a stream cipher is to use a pseudorandom key instead of a random key in the one-time pad. A pseudorandom bit string is a sequence of bits that for all practical purposes appears to be random. Pseudorandom bit strings can be generated with the pseudorandom bit generator. This is a deterministic algorithm that takes as input a relatively small random seed and outputs a longer pseudorandom sequence called the keystream. A pseudorandom bit generator can be used for encryption as follows. The randomly generated seed of relatively small bit length is a secret key shared by Alice and Bob. When Alice wants to encrypt a message for Bob, she passes the seed through the pseudorandom bit generator, which is a publicly known algorithm. The generator stretches the purely random seed into a much longer keystream that appears to be random. The keystream can then serve as a secret key in the one-time pad. And so the bits of the keystream are XORed with the bits of the plaintext, one bit at a time, to get the ciphertext bits. When Bob receives a ciphertext, he generates the keystream by passing the secret seed through the pseudorandom bit generator. And then he adds the keystream bits to the ciphertext bits to recover the plaintext bits. So a stream cipher emulates a one-time pad in the sense that the encryption and decryption processes are similar to the one-time pad, except that the keystream is a pseudorandom bit string instead of a purely random bit string. Note that unlike the one-time pad, a stream cipher does not have perfect secrecy. This is because the keystream is no longer purely random, but pseudorandom. And hence, security of a stream cipher depends on the quality of the pseudorandom bit generator. I should mention that one difficulty with using stream ciphers in practice is that we still have the requirement, as we did with the one-time pad, that keystream should never be reused. Suppose that Alice wishes to send Bob a message. She uses a secret seed that she shares with Bob to generate keystream of the required length and adds it to the plaintext to get ciphertext. When Alice wishes to send Bob a second plaintext, she can't reuse this keystream. Rather, she needs to continue to generate keystream from the point she left off after encrypting the first message. And so she generates a second piece of keystream and adds it to the plaintext to get the second ciphertext. So Alice and Bob need to keep track of which portion of keystream was used to generate a particular ciphertext. Ensuring that a portion of keystream is never reused can be problematic in practice. There are two security requirements for the pseudorandom bit generator used in the stream cipher. First, the keystream produced by the pseudorandom bit generator should be indistinguishable from a purely random sequence. This is the indistinguishability requirement. Second, we have to assume that the adversary knows a portion C1 of the ciphertext and the corresponding plaintext M1. Hence, the adversary can easily find the corresponding portion of the keystream K1 by adding C1 and M1. Thus, given a portion of the keystream, it should be infeasible for the adversary to learn any information about the remainder of the keystream. This is the unpredictability requirement of a pseudorandom bit generator. Let me remark that one should never use the Unix random number generators RAND and SRAND for cryptographic applications. RAND and SRAND work as follows. The user generates a random seed x0, which is a relatively small random number. From the seed, RAND and SRAND generate pseudorandom numbers x1, x2, x3, and so on. xi plus 1 is defined to be a times xi plus b modulo n, where a, b, and n are fixed and public constants. So the seed x0 determines the other numbers in the sequence x1, x2, x3, and so on. So, if an adversary learns any one of these numbers, let's say xi, then the adversary can very easily determine all subsequent numbers, namely xi plus 1, xi plus 2, and so on. So RAND and SRAND do not meet the unpredictability requirement. I'll next present the ChaCha20 stream cipher. ChaCha20 was designed by Dan Bernstein in 2008. Dan Bernstein is a very well-known applied cryptographer and also one of the world's best programmers. ChaCha20 is conceptually very simple. It's word-oriented, which means that it operates on 32-bit binary strings, and it uses only simple arithmetic operations, namely integer addition modulo 2 to the 32, exclusive OR, and left rotations. These three arithmetic operations are included in the instruction sets of most modern processors. As a result, ChaCha20 can be implemented extremely efficiently in software, and moreover does not require any special purpose hardware to improve its performance. No security weaknesses have been found in ChaCha20. And so, because of its very impressive performance and strong security, ChaCha20 has been widely deployed in practice, including in TLS. I don't have anything substantial to say about ChaCha20 security, since its design is not reliant on any underlying theory. Also, as I mentioned, no weaknesses have been found in ChaCha20. And so I'll just present to you a description of the encryption and decryption algorithms. From the description, I hope you appreciate ChaCha20's conceptual simplicity and also the fact that it can lead to very fast software implementations.
Here is an outline of the ChaCha20 stream cipher. The ChaCha20 keystream generator maintains a state. The state is initialized with the secret key K and an initialization vector, IV. During each iteration, the keystream generator produces a block of 64 keystream bytes, which are added to a 64-byte block of the plaintext to produce 64 bytes of ciphertext. Then, the state is updated. The process is repeated until enough keystream bytes have been generated to encrypt the full plaintext.
ChaCha20 has two components, an initial state and the quarter round function. I'll first describe ChaCha20's initial state. I'll need the following notation. The secret key in CHA-20 is a randomly selected 256-bit string K, which I've written as a sequence of 8 32-bit words, K1, K2, up to K8. There is a 128-bit constant F, comprised of 4 32-bit words, F1, F2, F3, and F4. These 4 words are written here as hexadecimal strings of length 8. Hexadecimal is base 16, indicated by 0x. Each of the 8 hexadecimal digits is between 0 and 9, or A to F. These represent the decimal numbers between 0 and 15, or a binary string of length 4. And so a hexadecimal string of length 8 can be viewed as a binary string of length 32. CHA-20 uses a 96-bit nonce n, written as a sequence of 3 32-bit words. A nonce, also known as an initializing value IV, is a non-repeating quantity. Nonces are usually selected at random or by incrementing a counter. CHA-20 also uses a 32-bit counter C. The initial state of CHA-20 can be represented by this 4x4 array of 32-bit words. The first 4 words is the constant F. The next 8 words are the words of the secret key K. We then have the counter C and the 3 words of the nonce N. So CHA-20's initial state is 512 bits in length. I'll next describe the CHA-20 quarter-round function. It's called a quarter-round function since it operates on a quarter of the state, so on a binary string of length 128 bits. The input to the quarter-round function is comprised of 4 32-bit words, A, B, C, and D, shown here at the top of this diagram. The purpose of the quarter-round function is to mix up the bits of A, B, C, and D in a complicated nonlinear fashion. This is done with 3 arithmetic operations defined on 32-bit words, namely XOR, this box sum operation, which is integer addition modulo 2 to the 32, and left rotation by t-bit positions. The result of each of these 3 operations is a 32-bit word. Here's how the quarter-round function is defined. First, the words A and B are box summed together to get the new word A. The result is then XORed with D to get the new value of D. And so on. The bits of A, B, C, and D are mixed using 12 arithmetic operations on 32-bit words. The output of the quarter-round function are the 4 words at the bottom of the diagram. Finally, here is a description of CHA-20's keystream generator. Suppose that Alice wishes to send Bob a message, which is 64,000 bytes in length. Each iteration of the keystream generator outputs 64 keystream bytes. And so Alice would need to iterate this algorithm 1,000 times to generate 64,000 keystream bytes. So, to encrypt the message M for Bob, Alice selects a nonce, preferably at random, and initializes the counter C to 0.
Alice uses a different nonce for each message she sends to Bob. The counter is used to count the number of times the main loop in the keystream generator is iterated when Alice encrypts a message. The use of a nonce and counter ensures that, with very high probability, Alice never invokes the CHA-20 keystream generator with the same inputs. This ensures that Alice never reuses keystream.
To generate the next block of 64 keystream bytes, Alice does the following.
Alice first creates the initial state S, which, you should recall, consists of the 4 words of the constant F, the 8 words of the secret key K she shares with Bob, the counter C, and then the 3 words of the nonce she selected for encrypting this particular message.
She then updates S by repeating the following 10 times. Alice first applies a quarter-round function to the 4 words S1, S5, S9, and S13. These are the 4 words in the first column of S. This invocation of the quarter round function mixes up the bits of the 4 words in the first column of S. The next invocation of the quarter round function mixes up the bits in the second column of S. Then the bits in the third column of S are mixed, and then the fourth column of S. The fifth invocation of the quarter round function mixes up the bits in the 4 words in the main diagonal of S. Then the bits in the second diagonal of S are mixed, and then the bits of the third diagonal, and finally the fourth diagonal of S. So after executing the quarter round function 8 times, the bits of the 16 words of S are mixed together in a quite complicated and non-linear fashion. This is repeated 10 times. After this is done, S and S prime are XORed together and outputted as 64 keystream bytes. Alice then increments the counter C and repeats the keystream generation algorithm to generate the next block of 64 keystream bytes to encrypt the next 64 plaintext bytes. If the plaintext message M is 64,000 bytes in length, then Alice invokes the keystream generator algorithm a total of 1,000 times, each time with the same nonce and different counter C. The 64 keystream bytes are XORed with the plaintext bytes to produce the ciphertext bytes. The nonce is also included in the ciphertext, since Bob will need it to decrypt the ciphertext. When Bob receives the ciphertext and the nonce, he regenerates the keystream bytes using the keystream generation algorithm just as Alice did. And then he XORs the keystream bytes with the ciphertext bytes to produce the plaintext bytes. We can now see why ChaCha20 is very efficient. To generate 64 keystream bytes, the quarter round function is invoked a total of 80 times. Each invocation requires 12 arithmetic operations. And so, 64 keystream bytes can be generated using only 960 computer instructions. ChaCha20 incorporates a nonce and a counter into keystream generation, thus ensuring that keystream is never reused, even though Alice and Bob might use the same secret key for a long period of time. Since they use a 96-bit nonce for each plaintext that they encrypt, and they increment the counter for each 64-byte keystream block used to encrypt a 64-byte block of a particular plaintext, with very high probability, ChaCha20 keystream is never reused by Alice and Bob.
We'll begin our study of block ciphers in the next lecture. We'll discuss some of the history behind the block cipher DES, which will include some gossip about the National Security Agency. I hope to see you in V2c.